Multimodal AI models like Gemini 3.6 Flash, Claude 3.5 Sonnet, and DeepSeek R1 possess an exceptional ability to reason. They can process vast amounts of data, analyze market conditions, and plan complex multi-chain workflows with high precision. But these reasoning engines share a structural limitation. By design, neural networks are probabilistic. They infer and predict, meaning the outputs are non-deterministic. The exact same input can produce different results across different sessions. Blockchain networks operate on the exact opposite logic. The standard Ethereum virtual machine relies on externally owned accounts, or EOAs, which require mathematically rigid, deterministic private key signatures to execute any state change. Handing a standard private key directly to a probabilistic AI invites disaster. A single hallucinated variable or an unexpected logic branch leads immediately to infinite drain attacks or the execution of irreversible rogue transactions. You cannot safely pair an advanced probabilistic AI agent with standard Web3 wallet architecture. The mathematics of neural networks and the mathematics of private keys do not align. Resolving this incompatibility requires a dedicated coordination layer. QMoosa Nexus is a protocol engineered to bridge the gap between AI reasoning and on-chain smart contracts. It operates as a translation engine. It takes the probabilistic off-chain intent proposed by an AI and forces it through a series of strict constraints, producing a mathematically bound, deterministic on-chain settlement. To enable autonomous operation, the protocol shifts from user-signed transactions to an architecture centered on agent-mediated execution, where every AI action is filtered through a secondary security layer. The first step in this architecture is eliminating the vulnerability at the source, the standard externally owned account. We strip away the direct private key. In its place, the protocol implements the ERC 4337 account abstraction standard. Specifically, it deploys a contract known as QMoosa SmartAccount.Sol, currently operating across networks like Base and Ethereum Sepolia. This creates a modular architecture. Instead of an AI holding a cryptographic key that gives it absolute control over the wallet, the smart account itself manages the custody, treating the AI as just one of many distinct permissioned inputs. Stripping away direct private key access is the technical foundation for granting an AI operational agency on-chain. Surrounding this smart account is the second layer, PolicyGuardian.Sol. This functions as an immutable sandbox that isolates the agent's actions. The AI must use structured tool calling commands, like prepareTX, to submit a proposed action. The Guardian then subjects the proposal to a series of deterministic filters. The first is a hard daily spending limit, metered precisely in USDT or the native QMS token. If the financial math clears, the Guardian evaluates per-transaction velocity limits and cross-references the destination address against a strict, pre-approved target contract whitelist. If the AI's proposal breaches any of these parameters, the transaction fails. The system triggers an automatic emergency pause or kicks the proposal to a human multisig for manual review. Inside this sandbox, the probabilistic AI merely proposes. The deterministic smart contract unconditionally disposes. A single agent operating in isolation is limited. Complex workloads require multi-agent swarms working in tandem.
Coordinating a swarm autonomously requires more than just a single random seed. It requires a shared, evolving state that every agent can verify independently. Standard decentralized randomness provides a value, but swarm coordination requires a common spatial model to track interactions. To manage this, QMoosa integrates John Conway's cellular automata as a decentralized entropy beacon. The cellular lattice allows the swarm to calculate its next state locally based on on-chain rules. Every agent can see how the collective is evolving without needing a central coordinator or an external oracle to dictate every individual move. This cellular beacon allows the swarm to achieve verified state coordination by transforming simple local rules into complex emergent group behavior. The final structural requirement is ensuring the system remains cryptographically secure for decades. Standard blockchain networks rely on elliptic curve cryptography, or ECDSA. As quantum computing advances, Shor's algorithm provides a mathematical pathway to crack these traditional signatures. QMoosa prepares for this by implementing post-quantum lattice cryptography. The protocol adopts two specific standards from the National Institute of Standards and Technology, FIPS 203 and 204. These standards divide the labor. MLDSA secures the signature validation, while MLChem manages the underlying key encapsulation mechanisms. Because lattice-based math relies on problems that quantum computers cannot efficiently solve, the autonomous swarm is insulated against future quantum adversaries. This linear flowchart illustrates the four-layer architecture working together to process a transaction. Imagine instructing the protocol's interactive chatbot to autonomously swap USDC held on the base network for SOL on the Solana network. First, the intent routes through the AI Agent Studio Planner, which calculates the most efficient multi-chain route. It then submits this proposal into the deterministic parameters of the policy guardian, ensuring it falls within daily limits and whitelisted addresses. Once approved and secured with a post-quantum lattice signature, the transaction data is compressed and routed into a succinct zero-knowledge bridge. These zero-knowledge proofs act as cryptographic receipts. They allow the QMoosa smart contracts to verify and execute state changes across differing virtual machines simultaneously, without requiring the destination chain to reprocess the full dataset. The pipeline successfully isolates probabilistic AI thought off-chain while enforcing strict quantum-resistant execution on-chain. Sustaining this cross-chain prover architecture requires significant computational resources, which necessitates a strict economic engine. This chart breaks down the immutable hard cap of 1,000 trillion QMS tokens. 35% of this supply is allocated to funding the ecosystem and building the autonomous agent economy. Another 25% is reserved for proof-of-useful compute block rewards. These incentivize the decentralized GPU provers running the network, governed by a 10-year halving schedule. Furthermore, the entire economic and operational framework is designed for compliance, adhering to the EU AI Act, the EU MICA regulations, and FATF travel rules. By utilizing account abstraction, cellular entropy, and lattice cryptography, QMoosa Nexus provides the blueprint for agent autonomy, granting multimodal models true operational agency through strict programmatically enforced boundaries.